Okay, so people are still coming in, but I think we can go ahead and start just to be prompt. We do have recordings of the session, so as people join in, they miss a couple minutes. That will be on our YouTube channel. So hi everyone, welcome to the Essex Seminar Series. I'm Kazi, I'm going to moderate the seminar today. So we're here welcoming Steve Nesbitt, who's going to talk to us about understanding the ingredients for a global convective hotspot in subtropical South Africa. So I just want to remind all of you that this session is being recorded and will be posted on our YouTube channel. So I'm going to go ahead and hand it off to Ralph for the introduction.
Yeah, thanks, Kazi. Yeah, and welcome, Steve. Steve's now the department head at the Department of Atmospheric Sciences, where he's been a professor for a bit. I've known Steve for a long time, back when I think he was still a student in some of the early TRIM and GPM days. He's a well-rounded scientist that does a lot of interesting work with field campaign data and also remotely sensed data. And I think I have he's got degrees from State University of New York in Oswego, then went on to Texas A&M, and then finally got his PhD at the University of Utah. One of many excellent scientists that were students of Dr. Ed Zipser out there in Utah. And it's good to see how well Steve's done in his career. So I'm going to turn it over to him and we'll learn a bunch of interesting things about these convective hotspots.
All right. Well, thanks very much, Ralph. And it's a pleasure to be here remotely from Urbana, Illinois. And I'll get started here talking about RELAMPAGO-CACTI, which was a field campaign that was conducted back in 2018 and 2019, right in the middle of Argentina. It's a place where there's pretty amazing convective morphology, as I'll talk about here today. And also it was, for this group, one of the first field campaigns or major campaigns that had GO16. And I'll talk a little bit about our use of that here in this study as well. All right, so a little bit about me. I grew up in upstate New York, and as Ralph mentioned, I have 3 degrees in meteorology, and then I went on to postdoc at Colorado State and joined the faculty here at Illinois in 2006. I have a textbook that I co-authored with Bob Rauber on radar meteorology, and I've been involved in a lot of field campaigns around the world, and have 3 sons and enjoy the outdoors. But a little challenging here in Illinois sometimes, but we figure out how to do it. All right, so as Ralph mentioned, I got my start in atmospheric sciences looking at data from the TRIM satellite. Many of you are probably familiar with that. It was the radar that had the first precipitation able radar to provide 3D scans of convective storms in the tropics. And part of my dissertation was actually looking at mesoscale convective systems around the tropics. And, prior to TRIM, we had really no idea how organized convection was in the tropics, comparing different regions like land and ocean. And one region we saw as a hotspot was the region down in South America, down here in the subtropics, in the lee of the Andes, where we saw the highest fraction of rainfall from mesoscale convective systems. Now, we've done a lot of work over the years, along with other scientists, including producing amazing videos now from the GPM iMerge products, looking at the morphology of different convective systems around the world. But this region in subtropical South America stands out not only from its perspective of having very organized convection, but it also turns out to be some of the most vertically intense convection. And so sort of my curiosity that came all the way from my PhD work into my interest in doing field campaigns led me to put together over a period of 7 or 8 years a project where we took ground-based assets down to Argentina and actually observed these processes with field campaign observations. So really one of the big science drivers of Relampago was this region where we have really organized convection. And for those of you that are familiar with general circulation models and climate models, we know that those coarse resolution models have to parameterize convection and its impacts on its environment. And that leads to many times large biases in producing precipitation, and then also the coupling between convection and the large scale. So we found this region in many studies, as you can see here on the left, to have very significant low biases in terms of producing precipitation from global models and even regional models, which led us to a lot of questions about how convection behaves in this particular region. So when we go down, think about, where intense convection happens. Of course, a lot of times in convective meteorology, we use an ingredients-based approach. And I'm going to give an analogy for those of you that have ever been to Argentina or are familiar with the culture. You know that meat and grilling is a big part of their weekend routine. So when we think about, as meteorologists, what goes into creating a convective hotspot, we think that geography plays a role. We think that instability plays a role. Of course, if you've ever tried to produce convective forecasts, you know that triggers are important. And of course, if you want high impact weather, you need vertical wind shear. And we think that that is an ingredient for intense convection. So it's kind of like if you were to do grilling, right? You need your grill, which is the right location. You need your fuel. You need a trigger. You need wind shear, which may be a special type of beef that you like, and that make your optimal ingredients for your best barbecue. And of course, when we were down there, we had plenty of barbecue, and here's one example of some of the volume of meat that we ate. And I apologize to any vegetarians here in the audience. But as you know, if you've ever been to an Argentine restaurant, the barbecue tastes a little different than in the US. And of course, the analogy is that in the US, we have severe storms, but we know that the most intense storms in the United States are dominated by tornado-producing supercells. But in Argentina, you actually see very few supercells, but you see a lot of hail, relatively few tornadoes. So here we're basically trying to go through our taxonomy of convective storms meteorology, analogous to why barbecue might taste a little different in different places, to try to understand what goes on with the clouds in that region. So if we think about the geography of central and subtropical South America, the ingredients in terms of the fuel oftentimes come from the fact that you have the South American low-level jet, which is kind of like our counterpart here in the Great Plains, bringing moist, tropical, unstable air poleward in this case. And of course, the terrain of South America is very different than in the Rockies, where we have very high mountains. The Andes are much taller and much narrower than the Rockies, excuse me. And then, of course, you have the synoptic pattern there where you have the upper level jet, which is actually stronger on average than in the Northern Hemisphere, blowing over the Andes and causing all sorts of interesting agiostrophic flows, which enhance the low level jet and also interact with fronts that come from the south and in the Southern Hemisphere, bringing cold air, kind of your classic class of air masses, leading to the initiation of strong convective systems. And it turns out that this special mountain range here called the Sierras de Cordoba, which is located at about 32 to 34 degrees south, is a place where, if you look at tracks of mesoscale convective complexes, is basically a hotspot for generating these systems. And these systems grow rapidly. Sometimes they cross the entire continent from east to west in terms of their size. And they also propagate, sometimes all the way into southern Brazil, impact a very wide range of society in South America. So basically, a lot of the challenge here in terms of understanding the convection in this region goes on to looking at individual processes that happen within organized convective systems. And we know from basic understanding of what controls the generation of organized convection, you can go back to some of the classic literature by Rotuno, Wiseman, and Klemp, looking at the interaction between the ambient low-level shear, the cold pools that are produced by the convective systems, and the updrafts and downdrafts, which of course lead to the production of these cold pools, which can help grow storms efficiently. Of course, you also throw in the fact that we're dealing with terrain here. So the terrain, as we'll see later on, really modulates the low-level shear, leading to some pretty extreme environments for organization. It also leads to stronger deep shear, and it also modulates the thermodynamics, as we'll see. So it leads to special regions around the convection where you see this rapid upscale growth. So these questions led us to the field phase of the campaign, and this sort of series of sister campaigns, RELAMPAGO, which stood for Remote Sensing of Electrification, Lightning, and Mesoscale Microscale Processes with Adaptive Ground Observations. This project was funded by NSF, also contributions from NOAA and NASA looking at lightning, and also GO-16 use in the field campaign. It was also funded by agencies in South America, including the National Weather Service, which is an important partner. And you may know Celeste Saulo, who was the head of the National Weather Service in Argentina. She's now the WMO president. And also CACTI was a sister campaign that actually was a longer campaign that looked at one particular site funded by the Department of Energy. And CACTI stands for Clouds, Aerosols, and Complex Terrain Interactions. And our region of interest was in this blue box. And we had a sort of a complement of fixed and mobile observations that I'll show you that helped us not only look at cases here near the Sierras de Cordoba, but we also drove over to near San Rafael, right next to the Andes, to actually look at hailstorms that impact some of the wineries in that particular region. So here's a list of all the team. You probably notice a lot of familiar names on this team. All these people were able to deploy to the campaign, and we had a very large group of scientists that helped sort of go through the proposal to the implementation and analysis phases. So we broke our science into 5 focus areas: convective initiation, severe weather, upscale growth of convection, lightning, and hydrometeorology. And we had 5 different sub-teams that designed observational strategies for a given case that we were about to observe each day to optimize the sort of data collection for each of those initiatives. But our broader goals were really to understand the interactions of convection with local and regional meteorology. And as you'll see, we had aerosol instrumentation as well, and also land atmosphere interaction sites. We had the National Weather Service involved to improve severe storm prediction in South America, and also to understand these storms in the context of regional and global climate. So, as I mentioned earlier, this project took place in 2018 to 2019, fortunately before the pandemic. We had a long-term observation site that extended almost a year, where we had 30 flux towers and hydrometeorological measurements across the area. CACTI brought a super site of observations to the Sierras de Cordoba that was nearly 5.5 months. And then we had a period of 49 days where we had intensive IOPs, where we had people deploying mobile instrumentation for each case. And this ended up being a very significant effort, bringing mobile radars and other instrumentation down to the field. And these were operated by students and other scientists, both from the North America and South America, and it ended up being a very great collaborative effort, and also in terms of workforce development in South America. We also had an aircraft that was also there for about 40 days. So we were able to get environmental and microphysical data at some of the storms. So here is our base site where the DOE site was deployed. It was deployed in the foothills of the Sierras de Cordoba, which you see running north-south here. This is terrain. We had a variety of fixed sites, including sounding sites that measured the low-level jet impinging on the mountains. We had fixed radar sites that looked at the growth of the convection off the terrain. And then here at the super site, we had a ton of surface-based and remote sensing instrumentation provided by the Department of Energy. Now, our mobile instrumentation included mobile mesonet trucks, which you see here. These are part of the University of Illinois farm facility, which is an NSF facility that includes the Dow radars here, pictured down here. We had 3 X-band radars and also a C-band radar that was deployed here downstream of the terrain. The DOE site had a suite of about 85 different instruments, including 3-frequency radar, wind profiler, surface fluxes, aerosols, LIDARs, etc. And then these are pictures of the fixed radars. One of them was deployed by Argentina up here at the top in Cordoba. And then down here is the CSU C-band radar. And there's me and two Argentine collaborators there. So I'm not going to go through, for the sake of time, all the instruments here, but we have a very, very comprehensive data set of both the storm environments pre-initiation, remote sensing during the events, and then also looking at the post-event adjustment to the convection. And then in cacti, there was a strong focus on column-based measurements over the AMF site, which I showed a picture of earlier. Scanning clouds over the ridges. We were very close to the mountains here. And then the aircraft were able to penetrate, at least during the early stages of the convection. Later on, the convection became way too intense for the aircraft, and they usually were well out of the way. But we have good pre-initiation measurements of the aerosols, and then some of the early clouds that develop, we have good measurements of cloud droplet size distributions and thermodynamics. So what did we collect? Well, here's a big table showing the events during the IOP. We ended up collecting 19 cases in 45 days. And a lot of these cases had actual convection develop, where we were able to collect good data, and we were able to collect a large number of soundings. We deployed surface mobile mesonet data over most of the events as well. So just to give you an idea of what some of these events look like, here is basically a movie playing at 4x speed or faster of what these events might look like. The blue dots are radars that we deployed. The yellow dots are surface weather stations that we deployed. And then you see the radars turning on and other mobile trucks going around. The white dots coming off are radiosonde trajectories. So we were able to launch radiosondes about every hour. And then you can see this line developed right over our network. Fortunately, we were able to forecast that. And these circles that you see are the dual Doppler lobes, where we're able to estimate 3D wind velocities. And of course, all these radars are dual polarization so that we can look at microphysical processes within these storms as well. So if you look on the left, here's a map of all the sites that we used during this field campaign. You could put a lot of miles on our trucks for sure, both in Cordoba down here. So showing where we put radars, where we put launch soundings from. Total, I think we launched about 2,300 soundings. And then down below where we went over to Mendoza for 2 cases. Here are just vertical profiles, pressures on the y-axis and time over the IOP. And the top panel here shows the time of each IOP. And these are from a certain radiosonde site, showing theta E. So the high values here you see in the red, those are the low-level jet events that came in. And then this is the V wind. So you see the low-level jet negative being our strong low-level jet events. And then the U wind shows the very strong vertical wind shear that we see in these cases, with the jet often exceeding 50 meters per second aloft, and low-level jets 15, 20 meters per second. So a lot of vertical wind shear to help develop strong updraft cores along with strong cape. So we were able to pretty much hone in on the Sierras being a focus for convective initiation here. And these are actually cases from prior to the campaign. We also see in this area that there's a lot of upscale growth that happens very close to the mountains. And that'll be a theme that sort of permeates the rest of the talk here, the fact that we're able to really observe both the initiation and upscale growth phase in the same location. Now, if you think about the Great Plains, a lot of times you'll get initiation over a dry line, and it might take 6 to 12 hours for an MCS to develop, let's say, even half a state or a state away. In South America, we actually find that the upscale growth happens very, very quickly, only in less than 3 hours. So we see these things develop very quickly into lines, compared to a similar climatology in the Great Plains. It's more than twice as fast. And the events oftentimes are much longer. So these things last sometimes up to 2 days, compared with, MCSs sometimes can last quite a long ways in the United States, but these things, once they form, they tend to propagate over much longer distances over South America. In terms of, I'm going to skip forward here a little bit. So in terms of some of the cases that we saw, here's one case on the 10th of November, 2018. On the left here, we see the 850 millibar winds, and you can see the strong northerly low-level jet coming towards our location here, located in the star. We see high values of theta E shown by the contours with that low-level jet, and that intensified into, during the day, such that when our convection developed, it had a pretty strong low-level jet. And then looking at some thermodynamic soundings here on the right, you see a skew-T diagram of a series of our 3-hourly soundings that we launched at the DOE site. And you'll see there's plenty of CAPE. It's elevated, but as we'll see, these cold pools are so strong that they can break most caps that are presented once the convection does initiate. And then you see the low-level jet here in the hodograph with a northerly flow, and then backing around to very strong mid-level flow in excess of 50 knots here at 6 kilometers. So in some ways, it's very similar to what you'd call a loaded gun sounding on the Great Plains. But as we'll see, there's a few wrinkles here that make things a little bit different. So for this particular case, on the left, you see GO-16 1-minute imagery, and you'll see outflow that comes into our region, which will develop a convective storm that develops right on the mountains. In the red here, you see all of our assets, including the Dows, the Scouts, and hail pads that were developed by Matt Cumgen to measure the size of the hail. And you'll see, the value of GO-16 here and looking at this rapid evolution, but you'll see just the amazing deepening of the storm going from just some cumulus congestus clouds to a storm that we observed to be about 20 kilometers tall here in a matter of an hour and a half. Now, in terms of radar, this thing obviously looks like it had a hook echo that developed and moved off to the east. And yes, it looked like very much like a upside down supercell if you were looking at this from the perspective of a Northern Hemisphere meteorologist. Here's a Northern Hemisphere meteorologist looking at this thing and taking a picture. And yeah, this was a massive updraft that was more than 10 kilometers wide. And RHI images show that it extended above 20 kilometers during this particular day. Some detailed radar imagery from the DOE site shows the storm initiating, and you can see the supercell forming here over a period of about 45 minutes. And then RHI scans through the storm show the very turbulent nature of this updraft here as the storm developed, and the strong bounded weak echo region and wide updraft here where you can see likely hail being formed and falling out. And some of our dual pole products, these are at X band, so there's significant attenuation going on, but here's our hook echo. You can see the reduced ZDR here, very much indicative of a hail core, and very strong LDR and reduced rho HV, which are all classic signatures of a large hail signature. The evidence that we have large hail is that the radar that we had out on the plains actually got hit by the hail, and it was more than 5 centimeters. But we do see that, very, very strong updraft here and very wide overshooting top that was associated with this particular case. But pretty much your classic supercell. It did not produce a tornado because the low level curvature of the photograph actually was quite weak. However, the deeper shear that was present was very helpful in developing this very wide updraft. Another case that we have, 25 January. So here, this was after our IOP, but this was our champion in terms of the amount of CAPE that was present. Some soundings here that were launched from our fixed site indicated above 5,500 joules of CAPE, very strong vertical wind shear, And right after convective initiation, this storm was already 18 kilometers tall. And here you see actually a photograph of this particular storm, and you see the splitting supercells here. This one on the left, we're looking east here. So this one is the strongest one that's going to move off to the northeast and produce a very wide convective core. But you just see the amazing amount of inferred vertical velocity there with this particular cell. A little bit later on, by 20 UTC, this storm grew upscale and moved towards one of our other radars. And here we are doing an RHI scan of this particular storm. And you can just see that this radar was looking right into the whale's mouth of this storm. You have a bounded weak echo region, and then you see just the really intense reflectivities that extend well up to above 17 kilometers. So we have over 50 dBz at 17.5 kilometers. That is much stronger than any storm that has been observed by TRMM in terms of that reflectivity at that particular height. So this is a pretty amazing case. And then this radar is already up at about 1 kilometer. So we're seeing echo above 21 kilometers MSL in this particular case. So just to go through a quick GO-16 view of this particular storm, Serras de Cordoba are here, and you'll notice there's pre-existing convection off to the southeast. And the convection starts to develop on the ridge and just grow incredibly fast. The amount of mass flux that's going into the upper troposphere here is pretty incredible from these really strong convective cores that are producing these overshooting tops. So incredible rapid upscale growth, producing very strong overshooting in the upper troposphere, but also producing very strong cold pools that are lifting tremendous amounts of mass from the boundary layer up into the mid-levels and upper troposphere. So I'm going to go a little bit forward here. So in addition to some of the observations, we are now doing a lot of modeling to try to understand some of the processes that are going on. And given the research team that's involved, they've produced a lot of papers that you can find across the literature. But one of the thrusts that my group has been working on is looking at using the observations to inspire quasi-idealized cloud model simulations of some of these cases. And so my student, Itinder Singh, who's now a postdoc with Sue Vandenhever out at CSU, started working on this. And we basically are taking a doubly periodic idealized cloud model and running it with the terrain included so that we can start to look at some of the mesoscale flows around the terrain. So here on the upper right, if you look here, you can see these black contours. Those are the terrain in the model. And then the colors here are the cape. Okay, and you can see the effects of the topography actually lowering cape due to entrainment that happens due to turbulence over the mountains. But you see that on the mesoscale, the low-level jet is actually being deformed by the terrain. And on the eastern and southern slopes of the mountains, you actually see a maximum of cape that develops due to the mesoscale flow around the mountain. Over here on the right, you see convective inhibition. So you see in that region, sin is basically reduced down to 0. Also, the mountains tend to cause there to be blocking in the low levels and actually a reversal of the flow because of the upslope flows that develop along the mountains. And that actually maximizes low-level shear here on the downstream half of the mountains. And it also goes all the way up to 6 kilometers. And so actually the mountains create this sort of special environment around them that tends to not only increase cape, but also reduce sin, increase vertical wind shear. And that explains why we see some of these strongest storms right in these regions about 50 kilometers downwind of these peaks. And that agrees very well with the sounding observations that we collected during the campaign. So with the model, we can start to look at detailed trajectories of where the airflow goes around the terrain. And so in this particular diagram, we're looking at the observed sounding from this particular day, and you can see where the trajectories intersect the terrain. You see the strong convergence along the lee side here, just downstream of the peak. And that agrees with where we see a lot of the convective initiation in these mesoscale regions of convergence. And then you see along here, the water vapor mixing ratio along the trajectories intersecting this level, and you see where the moisture tends to pool down here to the south. Now, the nice thing about these idealized models is that we can kind of crank down Mother Nature. So in this case over here to the right, we're actually turning the low-level jet in intensity down about half. What happens is we see the trajectories actually curve much more towards the middle part of the range. And in the model, we see convective initiation happening much further north. And when we look at a lot of the different cases in Relampago, we actually see that happens in nature, that when we have a strong low-level jet, the storms tend to form further south in the mountain. When the low-level jet is weaker, we actually see the storms forming here more in the middle of the mountain range. So we looked at this further and took a control sounding and modulated the wind profile over a variety of intensities, basically keeping the winds above 3 kilometers the same. And what we found is that when we have a strong low-level jet, we tend to see supercell thunderstorms develop. Whereas when we weaken the low-level jet, we see more mesoscale convective systems develop, which kind of argues that the low-level jet is a primary control on whether the storms form these isolated, more hail-producing storms versus these more organized convective storms. This very complicated diagram just shows the life cycle of these different storms over these different low-level jet intensities. And here you see the strong low-level jet down here. We see a supercell that basically moves directly east. Whereas if we come down to our weaker low-level jet, we see the storm moving more north and north-northeast. We see the blue line here, which is our massive cold pool that develops. And then you see radar reflectivity contoured here in the colors. And so what we see is that the low-level jet in this experiment ends up really changing the whole nature of the type of convection that you see. Now, if you take severe storms literature or a class in mesoscale meteorology, you'll notice that supercells in the Great Plains are often noted for having stronger updrafts compared to mesoscale convective systems. Well, it turns out in Argentina that we see that generally the storms that have a weaker low-level shear profile here actually have wider updrafts and larger, more intense cold pools. Now, what does that end up doing? Well, it ends up actually causing there to be much stronger updrafts because these cold pools are really, really intense. If we look at the buoyancy within these cold pools here across these diagrams, you're basically seeing the strong low-level jet experiment on the right and the weak low-level jet experiment here on the left. We see that the cold pools in the weaker low-level jet cases are actually much stronger. And that lifting ends up causing much stronger, broader updrafts. So these updrafts, in terms of their area, end up being much stronger than these supercell cases. So they're much broader, they're much stronger in terms of vertical velocity, and that ends up causing much more vertical mass flux in the case of these MCSs, not only because there are more updrafts, of course, along the edge of the cold pool, but also because each individual updraft are much stronger and broader. We think that the cold pool production in these cases, because of the interaction of these big updrafts, the wide updrafts producing wide downdrafts that produce very cold air at the surface, is something that's particularly unique for these particular environments. So what we think is going on here is that when we have a stronger low-level jet, we actually see a relatively weaker cold pool that leads to these relatively, these storms that behave like a supercell that move to the east like you would expect given the low-level shear profile. But in the weaker low-level jet case, we end up seeing very strong, wide cold pools, and these are deep cold pools as well, that produce these slabular-like updrafts that lead to wider convective cores, more vertical mass flux, which feeds back into producing more strong cold pools. that also leads to very rapid upscale growth of the convection into broader convective systems. Now, we've also made it a point of Relampago to work very closely with our South American colleagues, and there's a lot of publications that have come out of Relampago, but we've been very happy with our sort of collaboration on looking at modeling in South America, the use of data assimilation in South America, and also use of GOES and radar data in their forecast process. So very briefly, this is a paper that was led by scientists at the National Weather Service in Argentina, looking at different configurations of WRF. And it was interesting that the convective environments here actually produce very different biases depending on the configuration of WRF in terms of choice of planetary boundary layer schemes and microphysics. So in terms of evaluating skill scores, we actually found very different biases when we compared the rainfall produced from the WRF model compared to some of the microphysics schemes that were chosen in these three different simulations. So this informed them to help develop an operational WRF scheme that they're using across their entire territory. And in addition, they've been making great strides in actually using data assimilation and forecasting in real time. So we used Relampago as a test data set, and they're actually using a lot of observations in real time, including from satellite and from radar observations, to develop a 4-kilometer ensemble Kalman filter system. So some of this work is in collaboration with Eugenia Calnet, of course, who you're probably familiar with at Maryland, who's also from Argentina. But they've been able to use this information to have a pretty state-of-the-art ensemble WRF system that they use for their forecasts. So kind of in closing here, I want to make sure if you're interested in this study, we have a special collection in the AMS journals. I think it's up to about 35 papers right now. And we also have papers in some of the other journals if you're interested in some of the other aspects of RELAMPAGO-CACTI. In the future, we're continuing to work on this data. It's a gold mine, and I think there'll be many more papers that come out of this effort. But we want to, of course, continue to use observations to help constrain models. And we need to take the step of taking climate models and rerunning them during the Relampago period to see how they compare with the observations. Also for global high-resolution convective permitting models, how do they do compared to the observations? And then, of course, the process level study, we're still diving into a lot of the detailed radar data that we collected. And so we need to continue to work on these different cases because they do tell us what's different about convection. And of course, the important part here is that by learning about a new convective regime, we might be able to tell different things about other places in the world where we don't have detailed observations, like in Africa and also sub-Himalayan Asia as well, where we don't have a lot of great case studies to look at. So in summary, we have a very comprehensive observational data set of convective processes near terrain, which is something that we don't have so much in North America. And also we've shown that it's a meteorologically unique region that has interesting types of convection. And our future work will continue to analyze cases in more detail. And of course, I'm open to collaborations. If the data sets that we provided may be useful for your work, I'd be happy to talk about how we can use those together. But with that, I will leave you with the gracias and feature some of the other things that we didn't get to talk about today, including our education and outreach component, also interacting with students in the K through 12 arena in South America. So thank you, and I'll take any questions.
Thanks. So if you have any questions, just go ahead and raise your hand or unmute yourself. Everyone should be able to do that. Or you can type your question in the chat. Any questions?
Find my chat window here.
If you hit escape, you should be able to get the chat open.
There
There's
we
a
go.
question from Ralph in there. How might this work tie in with the future AOS mission?
Yeah, this is a great question. I think there's a lot of potential information here from these case studies that might help us understand sort of the strengths and weaknesses of looking at convection from the perspective of, for example, Doppler radar in space, which of course is going to be one primary sort of new thing that is going to be on AOS. Of course, these convective updrafts are so big that they're not going to be, sub-pixel resolution, which is good. But also some of these very intense updrafts are of course rare, and they're also very strong. So they're going to provide for a lot of attenuation at some of these wavelengths that we use from space. So the good thing is that we have lots of ground-based data to do satellite simulation studies, model simulations where we can forward simulate what we see in some of these field campaigns and project them into space. But I think, one of the primary things where these field campaigns help us is they teach us that, for example, sun synchronous orbits are really not useful for studying intense convection because it doesn't happen very often at our typical times, for example, in the A train window. So it really is important to have sampling either by, orbits that are polar off of those times, because all the action in Argentina happens between 3 p.m. and midnight most times. So it's important to have that, or have a inclined orbit that we can see things off of the diurnal cycle.
Thank you. Do we have any other questions before we wrap up?
Yeah, I'll give a shout out to George. Yeah, these are some storms that would definitely be over the top of some of the satellite missions that we've launched before. So it's pretty incredible to think about that, but it kind of argues that we maybe, if possible, to increase that ceiling above 20 kilometers to catch these rare cases, if there's no negative trade-off. Yeah, I see the question. There's a new Earth Ventures mission led by Sue Vandenhever. Yeah, this is the Incus mission, which is led by Sue at Colorado State. A couple of my former students are working with Sue on that mission. And the idea of that particular satellite is that instead of using Doppler radar to measure vertical velocity, they're going to use time differencing, so they can actually see the radar profile increase with time and height to estimate vertical motion in the upper parts of the cloud. And that satellite mission, I'm not involved in it, but it sounds very exciting and offers a potential lower cost option if we can deploy, radars such as those that are being proposed by, companies like Tomorrow.io and Formation. We could estimate vertical velocity more routinely using some lower cost or commercial based satellites. So I wish Sue and the team the best of luck. It's a challenging measurement because it requires a lot of precise geolocation, but it's very exciting to see the potential there to look at storms around the world.
This is Ed. Can I throw in a quick question?
Sure. Go ahead, Ed. How you doing?
Yeah, I'm really sorry that I missed most of the talk because I just came to check my calendar and it's been written for 2 o'clock without noticing the Eastern time. So anyway, you and I have talked about these things before, but I just thought I'd raise this again. Is the only thing missing in Kansas and Oklahoma to match this area of South America a 10,000 foot mountain range?
Yeah, that's a great question, Ed. So Ed's question gets at really why the environments like this exist in South America, and we don't see such rapid growth and also extreme vertical development in the US. Well, I think that sometimes we do see it in the Great Plains. It's just that in South America, the terrain is so good at anchoring these things geographically that it's much easier to go see these things in a particular location. I mean, I've seen cases in Iowa, for example, where you do see the sorts of presentation that you see on GOES that we saw in South America with these huge wide convective cores. But it just depends more on sort of the synoptic setup at a given time rather than having the terrain help lock everything in. So I think from a frequency standpoint, perhaps it may not be that uncommon in the US compared to South America, but I do think that it's just much easier to see these things where we were in South America at a particular location.
And also, I just want to add, Ed, we'll have a YouTube video of this talk up in just a couple of days. So if you want, you can drop your email in the chat and I'll just make sure that that gets to you, since you missed the first couple minutes. Do we have any other questions before we wrap up? George left a comment. Good satellite capture of storms that go 0 to 500 in 90 minutes is really challenging.
Yeah. Yes.
Okay, so if we have no more questions, I think we're good to wrap up. Ralph, did you want to say anything? I just noticed you're unmuted.
No, I just wanted to say, enjoy the talk, Steve, and good seeing you, and hope to see more of you at some point.
Yeah, for sure. Thanks for the
Yeah.
invitation, everyone.
Yeah, absolutely. Thanks, Steve, for coming to talk to us today. And thanks, everybody, for showing up. We're going to continue with our seminar series next week. I'm actually just finishing up that information, so that should be in everybody's inboxes by tomorrow. Well, thank you, guys. Have a good afternoon.
Bye, everyone.